This video presents an introduction to drilling and sampling procedures in geotechnical practice. A thorough knowledge of the tools and procedures is necessary for planning and executing an effective subsurface investigation. The extent and type of exploration depends on the specific project. For example, the design of a county road may only require explorations to a depth of 20 feet, while the design of the foundation for a high-rise may require knowledge of soil characteristics to a depth of a few hundred feet. At remote sites, all the necessary information may have to come from new soil explorations. In highly developed areas, the extent of soil exploration may be reduced based on information from the surrounding sites. The type of investigation is also greatly affected by the soil type and variability. A structure founded on a homogeneous layer of clay may require high-quality samples to accurately predict the amount and rate of settlement. But if the same structure is on soil consisting of pockets and lenses of clay, silt, and sand, information of greater value may be obtained by taking a greater number of less expensive disturbed samples to determine the location and size of these pockets and lenses. These views of alluvial sand and gravel deposits are shown to emphasize that even relatively homogeneous deposits can have complex interlayering and heterogeneity on a local scale. An appreciation of the inherent complexity of geological deposits is needed for planning or interpreting subsurface explorations. To perform an effective subsurface investigation, the project engineer must be familiar with the tools and procedures, understand the effects that drilling and sampling can have on lab and field tests, and appreciate the inherent uncertainties involved with characterizing subsurface conditions. Most subsurface investigations are performed using drill rigs of numerous types and sizes. Drill rigs can be classified into four basic categories: highway, off-road, over water, and portable drill rigs. Highway drill rigs, the most common, are mounted on the back of an industrial truck, allowing high mobility and minimal setup time. A highway rig is used for sites that are relatively level and easy to access. Off-road drill rigs are used when access to a site is unusually difficult. Typically, these drill rigs are either mounted on large rubber-wheeled trucks or on tracks. If an off-road drill rig cannot directly access a site, a helicopter may be used to move it into position. For soil investigations beneath bodies of water, an overwater drill rig must be used. Some overwater rigs consist of a customized barge where the drill rig is positioned in the center and drilling takes place through a hole in the deck. Portable rigs can be partially machine operated, as shown here, or operated manually. These rigs typically have a depth limit of about 25 feet, depending on the subsurface conditions, and are used when access by an off-road rig is impossible and the expense of a helicopter is not justified. In any drilling program, the first step is to check for all possible underground utilities or obstructions, and get an underground service alert clearance as required by law. No drilling should begin without this clearance, no matter where the site is. After the drilling is completed, all boreholes or piezometer installations must be sealed in accordance with state and local regulations. Here a highway drill rig will be used to demonstrate the general features and procedures that are common to all drill rigs. After the drill rig is positioned over a borehole location, the mast is raised and secured and the drill rig is leveled. If the rig is not level, the borehole will be angled, causing great problems in drilling and sampling, in addition to producing an inaccurate soil profile. The drill head, located near the bottom of the mast, is raised and lowered using hydraulic controls. The drill head is connected to a gearbox which enables the driller to adjust the rotation speed to suit the current drilling conditions. A number of cables controlled by winches run to the top of the mast and back down to the hole. These are used for removing or attaching drill rods, auger flights, or sampling tools. Many methods of drilling have been developed, but only four prominent drilling methods will be discussed here. These four methods are solid stem continuous flight auger, hollow stem continuous flight auger, mud rotary, and coring. The main purpose of all drilling methods is to obtain representative samples of the subsurface strata at different depths. These different drilling methods are individually suited to different soil and rock conditions, and thus, more than one method may be needed on a given project. The solid stem continuous flight auger method is the simplest drilling system with only two basic components, the drill bit and the auger flights. The drill bit is located at the tip of the drilling stem, with the stem consisting of individual auger flights connected together. When rotating, the drill bit cuts and loosens the soil, enabling the flights to lift the soil out of the hole. Variations of the two most common types of bits, the finger and fishtail, are pictured here. Flights of auger are typically 5 feet long and come in outside diameters ranging from 4 inches to 14 inches. The connections between the drill bit, auger flights, and drill head use male and female connections that are secured by auger pins. The borehole is advanced by hydraulically lowering the rotating drill head as the auger and bit penetrate the soil. Flights of auger are added to the system as needed. Upon reaching a specified sampling depth, the borehole is cleared of cuttings. The augers and bit are removed by a cable. A sampling tool is then lowered down the open hole to take a sample from below the hole bottom. After sampling is completed, the bit and flights of auger are lowered back down the hole, reconnected to the drill head, and drilling is resumed. This drilling approach only works for soils where the open borehole does not collapse. Hollow stem continuous flight auger drilling is similar to the solid stem method in that the hole is advanced and soil is removed by the flights on the augers. The primary difference, as seen on the right, is that the auger flights are hollow. This allows a sample to be taken by lowering a sampler down through the hollow stem, thus eliminating the need to remove the auger from the borehole. The basic hollow stem setup is shown here. The inner bit is connected to drill rods that run through the hollow stem, and the other bit is bolted to the bottom of the lead auger. While drilling, the inner and outer bits rotate together, cutting and loosening the soil at the bottom of the hole. The soil cuttings are carried upwards by the auger flights to the top of the hole. To sample, the drill rod to cap adapter is removed, and the drill rods in the center bit are withdrawn from the hole. A sampler is then connected to the bottom of the drill rods and lowered down the hole for sampling. After sampling, the center bit is reconnected to the drill rods, lowered back down the hole, and drilling is resumed. Hollow stem augers use two types of connections. The auger on the right uses a 2-key connection, while the auger on the left uses an octagonal connection. Hollow stem continuous flight augers typically come in 5-foot sections, with inner diameters from 2 1/4 inches to 12 1/4 inches. The outer bit has replaceable teeth, in which rollers and cutters can be inserted to adapt the bit to different ground conditions. The common inner bits are the fishtail and stepwise bits. The main advantage of hollow stem augering over solid stem augering is that the drill rods and center bit may be removed at any time to allow for disturbed, undisturbed, or core sampling. Also, the borehole is supported by the flights of auger, eliminating any possibility of the hole collapsing. This makes it possible to drill with a hollow stem auger in sands below the water table. Mud rotary, or rotary wash drilling, is very different from the continuous flight auger methods. The underlying principle is that mud, a mixture of water and bentonite, circulates through the borehole, bringing the soil cuttings to the surface and supporting the sides of the borehole. For drilling, a bit is connected to a series of drill rods that are attached to the drill head. Drill rods typically have an outside diameter of 1 5/16 inches to 3 1/2 inches and are attached together using connectors like the ones shown here. Common rotary bits include drag bits, roller bits, and plug bits. The replaceable drag bit, one of the most common, consists of a barrel, bowl, blades, and connectors. This design is economical since worn teeth can be replaced rather than replacing the entire bit. The cone bit has teeth on the surfaces of cones, which rotate as the bit is turned. The spacing and size of the teeth on the cone depend on the type of material to be drilled.